You still haven't come out? I'm still working on it. I'm still working on it. No, but I think we should I thought my daughter's just her 3rd year of high school. A big change in this high school. Yes. So independent well, that's the hard thing. I'm like, my wife calls me and she'll say, "Oh, I'm out shopping." I go, "Where are the kids?" Well, they're at home, you know. Remember, they're 12 and 14. They can stay at home on their own. That's right. That's right. Now with Facebook, everything turns out, and big garbage gets out of control. This is not a concern. The aerospace for him is the reality is too heavy. And you get from the mission model that we think that
Do you know how it can understand?
Well, actually, I've never used it, so I'm not too sure. Actually, I'm not very expert. No, I'm not. Absolutely no.
it work with your computer?
You can't try that for the moment.
No, I'm sorry. Everything's a meeting and some more.
That's the problem.
Yeah.
You can't really leave the department.
That's right. It's too close.
So it's,
It's too close.
So somebody
I don't really have much teaching. That's not the name.
probably also getting close to the end of the semester.
Yeah. And somehow things quite up. There's always one sense of the day also. Other people suddenly
already on.
So we have to wait for it.
No, no.
So let's begin. Today's speaker is franzke. And so he took his PhD 10 years ago, 2001 in Hamburg. And then went over to do 3 postdoc areas in the US, States, New York University, and Florida NCOR. NCOR is the main meteorological center in the US. But now since 2007 he is at the British Antarctic Survey, where he's working with stochastic volume measuring some on very long time scales like ice tides cycles and some short time scales like a few decades of temperature records in situ stations. So please, stochastic modeling, systematic strategies for stochastic climate modeling.
Yes. First, I want to thank the organizers of this really interesting program here for inviting me and also to let me speak about some of my not that recent work, kind of work which I did a few years ago when I was a postdoc with Andy Mine and Eric van den Eyck at New York University. And this is about how can we construct stochastic, low-dimensional stochastic models from large-dimensional dynamical systems. Lots of interesting systems are kind of high-dimensional, but most situations we are only interested, say, in large-scale or coarse-grained aspects of the system. Like if you are interested in climate, and we're not really interested in if there's going to be a cyclone in 10 years' time over Stockholm or not, then we are more interested if, say, the so-called North Atlantic Oscillation is going to be over a very long period of time in its positive or negative state. And the North Atlantic Oscillation also evolves on much slower time scale than say, individual cyclones. But of course, the state of the North Atlantic Oscillation then also has a very strong impact on, say, typical paths of cyclones. And that not only applies to the climate system, but also to other dynamical systems of really practical interest. And one of the typical features of those systems is that there are interactions between many different spatial and temporal scales. And as I already mentioned, in most situations we are mainly interested in the large scale or the slow aspects of those dynamical systems. And so there is kind of a need to come up with coarse-grained models to predict the temporal evolution of those high-dimensional systems. And this kind of calls for the development of low-order systems. With low-order, this doesn't necessarily mean just a few modes. Could be maybe 100 modes if we look at a climate system, which we could say has 10 to the 8, 10 to the 9 degrees of freedom. So reducing this to maybe just a few hundred or a few thousand would already be a huge step to make maybe lots of things we're interested in more feasible to compute, and maybe that you could also use low-order models for data assimilation, so that you take the observations and assimilate it into a coarse-grained system. Then you might be able to take those, say, initial conditions to start doing the predictions with the full or the high-resolution model. Okay, just I guess most of you kind of know the typical processes and time and temporal scales in the atmosphere that we have on really micro scales on a few meters or even less centimeters, turbulent eddies. Then we have, of course, boundary layer processes, convective systems, synoptic weather systems, and on larger scale, temporal and spatial scales, teleconnection pattern like the North Atlantic Oscillation, or then also the coupled atmosphere-ocean system. And the point I want to make, say, if you're interested, say, only in teleconnection patterns or coupled atmosphere-ocean modes like ENSO, then we are not really interested in the exact evolution of synoptic weather systems or connective systems. So I'm asking here the question, can we kind of treat those processes as a stochastic force to the evolution equation which we might derive, which only predicts the state of the North Atlantic Oscillation, which I'm going to focus mainly on in this talk, or maybe ENSO. But of course, you could also say we are interested in mesoscale connective systems, and then we could treat the boundary layer processes or small-scale turbulent eddies as some kind of stochastic force to predict connective cells, for example. I mean, the method I'm going to introduce kind of only assumes that there is some kind of timescale separation between the processes we are interested in and the faster timescale process. But of course, as we all know, there's not really a really huge timescale separation between those different processes, and most of them kind of overlap with the others. Okay, as I already mentioned, current NWP systems have about a spatial resolution of about 10 to 50 kilometers, and climate system models probably 100 to 500 kilometers. And this still means that many dynamical processes like convection or cloud physics still cannot be explicitly resolved. And another problem is that the time set in those numerical models is usually determined by the fastest time scale which is resolved, which in climate is also mostly the smallest resolved spatial scale. So even though we might only be interested in the large-scale temperature fields, we still have to run the climate models with a rather tiny time steps because we have to resolve lots of those small scales, even though we are not explicitly interested in them. And this kind of lets me ask the question if those smallest and fastest components resolved, say, in climate models, can we treat them as a stochastic process? This would potentially be computationally more efficient because we can run the climate models with a larger time step. Then this also would be a novel way to parameterize unresolved degrees of freedom because the traditional deterministic parameterizations rely on the law of large numbers. And so you basically come up with a bulk parameterizations. If, say, the large scale circulation is in a certain state, has a certain amplitude, then we infer kind of how the small scale processes should evolve according to the large scale. And of course, if you would look at scatter plots between large scales and the non-resolved modes, then you see a lot of scatter already. That would call that we kind of introduce some kind of stochastic force into the model. And the other problem is if we now go to finer resolutions, then we get into the situation that certain processes are now partially resolved. So, for example, convection, the traditional parameterization kind of assume that in each grid box you might have on the order of a few hundred or a few thousand convective cells, but now we might be in a situation where we have in a grid box only 10 convective cells, and then basically this law of large number, or the parameterizations which basically rely on the law of large numbers, that we have lots of small scale processes in a grid box kind of break down, and also stochastic forcing might be one way to improve the parameterizations. There's already a long history of stochastic climate modeling approaches, which was first attempted by Hasselmann in the 70s. And most of the approaches are more or less empirical approaches where we kind of fit some kind of either linear models to directly to the data, like linear inverse modeling, which is kind of a multivariate AR1 process. Then there are some studies who also introduce some nonlinear aspects into stochastic modeling, like multiplicative noise, which is a state-dependent noise, whereas those studies basically have state-independent noise as a driving force. And then over the years, also the models got more and more complicated with, say, also deterministic nonlinear parts and then some noise driving. But these are more or less empirical approaches to this. So you kind of take either parametric approaches where you predefine some functional form of the stochastic models, like just some linear deterministic part plus additive white noise forcing, or you assume that there are some kind of a nonlinear structure. And there, in the 60s and 70s in statistical physics, Mori and franzke, they were the first which kind of attempted to come up with a more formal way to do model reduction, say going from a high-dimensional dynamical system, how you then derive low-order models. But it's a very nice formalism, but it's very hard to actually put this into practice. And then Andy Mider came up with a procedure which is more or less easy to implement and also apply to, say, climate models. But this method kind of assumes that there is a timescale separation in the system, which this formalism actually doesn't apply, but because it doesn't require it, it's also not very useful for practical application. okay, to put this onto some more mathematical footing, we basically consider this the following dynamical system. We have two kinds of variables. Alpha, which could be a vector of dimension n, and beta, which could be a vector of dimension m. And they both evolve according to some nonlinear functions which depends on alpha and beta. And the only difference between alpha and beta is that they evolve on different time scales, where alpha are the slow modes and beta are the fast modes. So the idea is now that we come up only with an equation or evolution equation for the alpha modes. So to formalize this, we introduce a parameter epsilon, which determines the time scale separation. So in the limit that epsilon goes to 0, we will have infinite time scale separation between the alpha modes and the beta modes.
So this is not a square, it's just an index on H.
That's an index. Say I have a function of 1, which only depends on the alpha modes, and then I have a function of 2, G2, which depends on alpha and beta. I mean, these are two different functionals, which could have arbitrary form right now, and the same here. It's only to distinguish between those terms. And we introduce here the time scale separation parameter. And the term which only involves the fast modes, they actually evolve on a much even faster time scale than those two tendency terms. And now we ask the question, say we only know statistical behavior of the fast modes, the beta modes. Can we come up with an effective equation which describes the statistical behavior of the solute of the slow modes, of the alpha modes? So we don't try to attempt that we come up with a model which would show some pathwise convergence. We are only interested in an effective model which reproduces the statistical behavior of the slow modes, say the probability density function, the autocorrelation function, and variance, and so on. But only the statistics, and not really pathwise conversion. So this basically means we attempt to derive in a systematic way effective equations which could have a deterministic nonlinear term and a kind of a stochastic term which might depend on the state of the system. And dW is the so-called Wiener process or Brownian motion, which kind of is the driving force of this equation.
So alpha is determined by the largest eigenvalue of the system, I suppose. The evolution of alpha, the linear evolution of alpha.
Not necessarily eigenvalue. If you would, say, if you simulated the full system, then you would have information over all possible alpha components, and you could just look at the autocorrelation function. And those alpha modes, the autocorrelation function of the alpha modes would decay much, much slower than the beta modes. If it would be a linear system, then you would have in the eigenvalue spectrum some gap. But of course, if we have some kind of a nonlinear system, I'm not sure if this would still be the case.
That's at least normally the standard procedure, that one eliminates the modes which are governed by stable eigenvalues. Then one can eliminate the time dependence.
Yeah, in a way, that's also how we're going to do it. I mean, we use EOF, but you still have to check if the autocorrelation function is there really a difference in the time space or not.
Yes.
Because in most realistic systems, you wouldn't find any gap.
No.
And the motivation here is, say, this kind of depicts the evolution of one of the alpha modes, which is very smooth and also evolves on a very slow time scale. And if you would just write down a numerical model to predict the evolution of this, you could use a rather long time scale, say delta tc, for say on a climate time scale. But say the beta modes, they evolve much faster. So you would need to use a much slower, much smaller time step than the TF for fast mode. But on this time scale we can use for the slow mode. This basically this, even though it's deterministic, the beta evolution. On this time scale you can assume it's basically decorrelated, and you can kind of treat it as random. If we know the state of here or perturbation here, until we are here with the system of the beta modes basically has forgotten the state it was in here, which isn't really the case for the alpha modes. And that's intuitive idea behind the regulation of the effective model. So if there is time scale separation, then you can treat the fast modes effectively as some kind of a random process. Okay, we are now interested, say, in climate or geophysical fluids, and then they usually have a typical form so that we have some kind of a forcing function which doesn't depend on the state of the system, but some linear term, say the Coriolis force or linear dissipation, and some quadratic nonlinear term. And we also have in most systems energy conservation, which is basically this property. Now we just split the state vector x into slow and fast mode, and then just write it down in this form. The sweat terms, they are only the interactions of the slow mode, the alpha modes, and then we have here the linear driving of the slow mode for the fast mode, or some nonlinear terms, and the same for the evolution equation of the beta terms. And again, we put 1 over epsilon in front of those terms involving the beta modes. And again, for this term, we say it's 1 over epsilon squared. So this term evolves even on a faster time scale than those terms. Now we make so far everything is still exact. Starting from the equations of motion, the only thing I did is that I split up the state vector into 2 components, which still could be vectors, and just wrote it down in a very long form. And now we assume that this term, which evolves on a very fast time scale, that we can represent this explicitly by some stochastic forcing. For example, an Ornstein-Uhlenbeck process. Say we would have a linear damping of the state vector beta plus some random noise, but actually we don't really have to specify the function or the form of this random process. Just assume that this is now some kind of a random process here. If we now do lots of mathematics, lots of algebra, then we can derive, in the limit that we have time scale separation, the effective equation. I don't want to go into how you actually derive this here, but I'm very happy to talk to everyone maybe after the talk or later this week how you actually can derive this kind of equation. And actually I also show a very simple example where you can actually derive this analytically in a few slides later, but it's a very simple example, and this, in the general case, this would be more involved. So basically, that's the so-called Baire truncation. That's basically survives from the original equations of motion. Then we have a set of deterministic correction terms. There's some additional forcing term, some additional linear component, additional quadratic nonlinear, and then something structurally new, which would be a cubic term. And this term basically arises from the interactions of the slow with the fast modes. And then we also get 2 kinds of stochastic forcing term or noise terms. One would be a state-independent noise, and one a state-dependent noise.
So, Christian, can I just check? So
you've just got diffusions there for the last two terms. It's the idea that the second line has corrected the systematic effects in the truncation. So you've just got DWs. You could have had Ornstein-Uhlenbeck processes at that level, but does the math suggest that the second line actually corrects the systematic effects so that you can replace all random processes at the alpha level with pure diffusions?
There are no reinforcing terms in this equation. It's only this term.
Yeah. So if you model that bottom term with an Ornstein-Uhlenbeck process,
Yes.
okay, so imagine there was a systematic effect
Yes.
over time, right? Then is it still the case that when you get back to the next slide, you only have diffusion terms, you only have Brownian motions in the stochastic component?
Yes.
Right.
I think it's going to become clearer when I show this really simple example, because then you see how, basically we integrate over this equation, where we basically get a solution for beta of t, and then we get here an integral over the stochastic terms and all those integrals over the deterministic terms. Then we just plug it into this equation and you just see, I mean, in a way, those deterministic correction terms, they kind of take account of systematic effects. I mean, you could see this as some kind of nonlinear damping.
Yeah.
So this is completely to put eddy correlation.
Yes.
Called what?
Eddy interaction.
At the moment,
But those eddy interactions also produce this multiplicative noise. So you can't really split those. I mean, if we have this cubic term, this also implies we have this state-dependent noise. Also, if we have state-dependent noise, then we really need to have the cubic term. I mean, they arise from the same interactions between the alpha and the beta mode. You can't really split. I mean, it's only the way I've written it down, so first the deterministic and then the stochastic terms, but you can't really split them up. One requires the other. And also I've written it down in Ito form. This means this term already kind of also contains the noise-induced drift. For those people who actually know the difference between Satonovich and Ito. Basically, Ito means that the noise is really IID. There's really no correlations of the noise structure. And Satonovich would be in the case where we still have a finite correlation length in the noise, which would be more appropriate for physical systems. So that's also an assumption I have to make in the example I'm going to show you in a few slides. But you can always switch between those two stochastic entities.
You didn't write down any explicit spatial dependence, but that's what you have in mind later, right? There's no space dependence here in your model. It's ODE.
It's ODE, but
you later want to apply it to PDEs, right?
yes, but we project it onto basis functions, so we transform it into an ODE.
Yes. Well, that's what you did already, you say. Right.
We're going to use EOF. So
that's what the index I, but the index I can refer to all kinds of other things.
Yes, I mean, you could also still have space dependence in the system. Right now, it's only about the temporal evolution and
because people mentioned discuss the diffusion or something. But diffusion really only probably makes sense if you have a spatially extended system. That's what I would understand under diffusion.
So I think we would use diffusion within a stochastic calculus just to mean the Brownian motion term.
yes.
Right.
But I think explicitly it's a Brownian motion term rather than integrated Brownian motion term. So it's really a white noise process. Yeah, there's definitely two different diffusions going on here.
Yeah, I see. Okay.
Okay. To derive the effective equations, the only assumptions we have to make is about the term involving the fast interactions of the beta mode. So that's agotic and mixing, and that we, as I already mentioned, that we tend to present this by stochastic process. And in order, and the theory so far only gives us the functional form of those correction terms. And now we basically have to calculate the numerical values of those vector or matrix elements from the statistics of the fast modes. And to do this, we only needed to have estimates of their variances and correlation functions of the fast modes. So in this method, we don't really fit any information or any direct information of the slow modes. Only we introduce the statistics of the beta modes to basically estimate the values of those terms here and the noise terms. Okay, as I basically said, that the mode reduction kind of comes up with the closure terms for the reduced model, and we only need the information, the statistics of the fast variable. And this is kind of in contrast, say, to autorecursive process or linear inverse models, which directly fit the reduced model from data of the slow modes. And some even linearize the dynamical equations, whereas we try to touch the dynamics of the system. And this approach also has the advantage that we can interpret
So what you mean that you are not going to do any fit into data here? You're just starting with a complicated set of equations and deterministically arrive at a order model without any data fitting.
And this derivation also gives us equations how to calculate the order. Those symbols here, H would be a vector, this would be a matrix, a tensor, and so on. So we have to estimate all those vector elements from the data. But we already have equations how to do this. Basically, we only need to calculate the integral over the autocorrelation function and divide by the variance, for example. I mean, it's not that we need to come up with a fitting procedure to estimate the tensor elements. The theory already predicts how to do this. So in that sense, we kind of fit the data, but it's predicted by the data how to do it instead of, say, an AR1 process. Then you just, I mean, that's a very general framework, and then you just have different or some kind of way to fit it to data. But you also directly fit it to the data you actually want to predict later on.
Could you say that you're running the full complex model and use that data? That model tells you how to.
You can see this as some kind of a turbulence closure. And it already predicts how you actually close the system. Okay, so we can also interpret or physically interpret the corrections terms, say the linear interactions of the fast with the mean set produce additive noise and a deterministic component to the linear term. So the driving of the slow modes by the fast modes would introduce some additive noise and also a component of the deterministic linear term. And the advections of the slow modes by the fast modes, they produce the multiplicative noise and the cubic term. So later on, we then can actually look which of those interactions are actually important in the system we are investigating. Okay, maybe that's going to put it onto more. Maybe that helps to understand what we are actually doing. Here I've written down a very simple low-order model which has some features of the atmosphere. Basically, we have linear damping and nonlinear terms which conserve the energy. So we have, again, linear damping, some forcing, and we have the linear nonlinear interactions between the resolved modes, which would be x1 and x2, and the fast modes y1 and y2. And the same for the fast modes, and they are directly driven by noise. I mean, if you take this term, that these are basically Ornstein-Uhlenbeck processes. And if this would be a climate model, then we actually would have lots or hundreds or even thousands of those Y modes. And here, intuitively, you can imagine that due to the noise components, we already account for lots of them. And so now we have only 4-component toy model, and then we can actually derive the reduced model analytically. And we do this, I only explain this for Y1, by basically solving the equation for Y1, which basically means I take this equation here and integrate over time. Then I can just formally write it down here. I have some initial conditions, then I have to integrate from 0 to time t over this term, and also have an integral over the noise.
Sorry for my ignorance. Can you just quickly write down what this stochastic process is you can refer to?
You mean this?
Yeah.
That's just or the derivative of Brownian motion.
The derivative of Brownian motion.
Yes.
Very good.
If you just look at this part, I mean, that's basically an Ornstein-Uhlenbeck process.
That doesn't help you.
But it's the continuous version of an AR1 process.
Okay.
So take an AR1 process, which is xt is rho xt minus 1 plus noise.
Yeah.
And imagine
That's basically a
it's very small.
damped oscillation driven by noise.
Okay.
And that's a damping term minus what gamma 1 y1 plus some noise.
The probability distribution of the noise, is that actually important here? It doesn't have to be Gaussian, or where I put it in there.
So for this
Doesn't matter, yeah?
we assume it's Gaussian.
Yeah. But would it actually matter anywhere in the end? For the
It's
formula.
hard to say in general. I
Okay.
mean, the whole framework, we don't really have to specify the form of the noise process.
Mm.
I mean, you could also have here a more complicated noise forcing.
Mm.
I mean, for those simple models, then you could probably still derive everything. If you want to apply this for a climate model, then it's very hard to actually say that's really the noise component, this has this PDF or this density function, and then we just assume it's Gaussian. And we hope that all deviations from non-Gaussianity actually are created by the nonlinear terms. But that's an assumption. Okay, we solve this equation by integrating over time. And we are now interested in the long time statistic behavior of the system. So this means that this term for t goes to infinity, goes to 0, so we can basically neglect this term. Then we can solve the next term just by integration by parts. Then we get this solution here. And then we can also show that this integral over this noise term basically is itself kind of more or less approximately white noise. Also in the limit that we have timescale separation. Now we take those two terms and go back to the equation for x1 and x2 and plug them into this equation. Wherever there's y1, we put in those solutions, and also for y2 here. If we can solve this equation in the same way and get the solutions for y2 and plug them just into those equations, and then we get a reduced model, which now only contains two resolved modes, and these are this is still the bare truncation with the interactions of only the resolved modes x1 and 2. Then we have the correction terms, also now only in terms of the x1 and x2, and also the noise triangle. Here we have multiplicative noise, state-dependent noise, and here we have additive noise, also one component which is state-dependent. Now we can look how well this reduced model actually does with reducing the full dynamics. And we do this by looking at the autocorrelation functions and the so-called third order moments, which is a measure for deviations from Gaussianity, and which is given by this formula here. Okay, there's a black line in those plots, that's autocorrelation, third order moments, and that's time lag here. The black line is the dynamics from the four-mode system, and the red line is the reduced two-mode system. That's both for I think the x1 variable, but would be very similar for x2. And in the case where epsilon is very small, 0.1, then both lines kind of overlie each other. This means in the case where we have timescale separation, or where we are very close to timescale separation, the system will produce the statistics of the full system very well. And if we go to larger values of epsilon, where we have say, moderate timescale separation or no timescale separation at all, then we see stronger deviations between the reduced and the full system. But say for the deviations from Gaussianity, at least the deviations in the same direction, which gives us some confidence that we actually can apply this data to climate model where we don't have timescale separation and still get some reasonable results.
Christian, what is the explanation for the fact that the deviations are all in the early part of the interval, but for all those pictures?
If you go to longer and longer time lags, say, this, in the autocorrelation function, then you assume it goes to zero. So if you have a perturbation to the system, after a while, it just goes back to the equilibrium.
So your dynamic model has no long-term memory?
No.
Okay. It's been constructed like that?
It's Markovian, it has a Markovian property.
Is that because of the stochastic terms in the false nodes?
To predict the next data, only the x t plus 1, I only need knowledge of x of t.
But that's a different property. I mean, long-term memory can be a property of Markov processes. It's just about how you write down the equations, isn't it? If you're
Do you mean memory or time scale?
Well, memory, I suppose memory in the sense that we can construct processes that are stochastic, that have very long, that do actually have very long correlations. Linear plus noise, for example.
Yes, if you have a AR1 process with the correlation coefficient close to 1, then you would also have a very long time scale, but it's still a Markov process, so you have a memory depth of 1.
Oh, I see. So effectively what you're saying is you're just taking your time scale longer than the characteristic time scale of the system, and that's why everything goes to zero.
Yes. I mean, I could. I hope that's clear. I mean, we basically wanted to decay. I mean, that's actually something we have to assume that the autocorrelation function decays to zero after some lag. Because we basically have to estimate the integral over the autocorrelation function and this integral and this two integrals basically have to converge to a finite value. If it would have long-term memory, then this would go to infinity. Okay. Here we just compare the joint probability density functions in the space of x1 and x2 for the full system, the four-mode system, and the reduced system. And I think we underestimated the peak a little bit, but the shape is very similar in the case that we have timescale separation, and we also get quite good results for the situation. The epsilon is larger. Okay, now we wanted to apply this to a more realistic time or circulation model, and basically want to derive some model which kind of predicts the state of teleconnection patterns like the North Atlantic oscillation. And I probably don't really have to explain here what the North Atlantic oscillation is. That's basically there's a large-scale pattern over the North Atlantic which has a strong influence on surface weather over Europe and the US, and it can be represented just as the normalized sea level pressure difference between Iceland and the Azores. And in the so-called positive phase, we have more storms traveling over the Atlantic towards northern Europe, so that the winters get wetter here and much drier over the Mediterranean, or vice versa in the opposite phase. Just to emphasize here the temperature impact of the NAO on precipitation, say this is the North Atlantic oscillation is also part of a more hemispheric mode, which is called the Northern NR mode, or the Arctic oscillation, which would have a more hemispheric impact. And you see, if we are saying the positive phase for a certain amplitude of the NAO, we have much warmer temperatures over Europe and also more precipitation, say over Scandinavia, and less over the Mediterranean. And if we flip the sign of the NAO, then also the anomalies flip the sign. But this motivates that if we the usefulness of some model of say the North Atlantic oscillations, which doesn't require really the resolving all the say synoptic cyclones and or convective cells. Okay, so to demonstrate that we can apply this to circulation, to a somewhat sophisticated circulation model, we use a quasi-geostrophic model, which is a spectral model introduced by Marshall and Molteni, serving the quasi-geostrophic equation. We use this with a T21 resolution, which is roughly 5.6 by 5.6 degrees with 3 vertical levels, and we force this model, this would be those S terms, but by forcing, which is empirically determined from the observation, so that we can reproduce the reanalysis data we use to derive the forcing as closely as possible with such kind of a very simplified version of the atmosphere. Okay, here is the stream function field displayed for the ECMWF era 40 reanalysis data. And this is a measure of the storm track, say the high pass filter standard deviations of 500 hectopascal stream function. And this is the circulations we are able to produce with the quasi-geostrophic model. And the stream function fields are quite similar, and also the storm tracks are very similar to the ERA 40 reanalysis data. And so from now on, we will just see this as our truth. And now we try to derive a low-order model which produces certain aspects of this quasi-geostrophic model. Okay, the first question we have to answer is how do we actually identify the slow modes in this system? And the standard way of doing this in atmospheric or climate science is the use of empirical orthogonal functions, which are also known under lots of different names in different fields of science, like principal components, turbulent low-F modes. And what this does is you take the set of observations and calculate the covariance matrix, and then you just look for the directions in phase space which explain the highest variance, and this would be the leading EOF mode, and then you repeat it to identify the directions with the second highest variance and so on. So this basically gives you a family of empirical functions which maximize variance. Then something introduced by Hasselmann and also used quite widely by franzke, so-called principal interaction pattern. This is a way where you try to find patterns of the circulations which capture the dynamics of the system by say, minimizing the difference between the tendencies if you would take those patterns and plug them into the equations of motions and the full system. Then you can also just look at, say, the zonal mean and derive some reduced model predicting you the zonal mean, or something which was introduced by Tim, the optimal persistence patterns, which have the property that they are very persistent. And while we have kind of a large family of different approaches to find the nice basis functions or patterns for our problem, that they have different advantages and disadvantages, so this is still some kind of unsolved problem which still needs further work. And for the rest of the talk, I just focus on empirical orthogonal functions. Since they are very easy to compute and also widely used, and say that the logarithmic oscillation can be represented by just one UF mode, which is also one advantage. Okay, now we take our UF modes, say the NAO-PLA, which would be represented by UF mode, and the nice property of UF is that they're also basis functions. So we can take our PDE for the QG model and project the equations of motions onto the UF modes, and then we get a set of coupled ODEs. And we also choose the UF in such a way that they conserve total energy. So this means that the total energy by the nonlinear operator in the QG model is also conserved, and that ensures nonlinear stability of the reduced system. Now we have to come up with or to split the UF modes into slow modes and fast modes. Okay, that's just to show you, say that the first UF mode kind of captures a huge part of the observed PNA, where we have some center of actions here over the Pacific and then kind of a wave plane over the US. And the second UF captures a lot of the major dipole of the NAO here. Okay, now how do we decide where to cut off the UF which we want to retain in our reduced model? And for doing this, we kind of calculated autocorrelation time scale for each of those UF modes. And each UF also has an expansion coefficient which describes the temporal evolution, and then we can calculate the autocorrelation function and then just calculate the autocorrelation time scale. And you can see here that the modes which explain most of the variance also typically have much lower autocorrelation time scale than all those training UF, with one exception, which is the last UF mode. But this mode explains basically zero variance, and that's kind of a spurious mode. But we can just neglect this for the remainder of this talk. That's why we don't really have a time scale separation here. There is maybe some leveling off at about 10 UFs, and we basically cut it off at 10 and then just look how well our reduced model we can do. And we actually also tested reduced models with just 4 UF, 6, 8, and 10. And the first thing we looked at, how well can the reduced models reproduce the observed variance distribution, the geographical distribution of the variance. This is the QG model and this is the stochastic model. And you can see that the structure is roughly the same. So we have some enhanced variability over the Atlantic and also here over the Pacific, but we underestimated the variance by a factor of 2 or 3 here. But if we just look at the structure of the pattern, that's very well captured by the stochastic models.
Question, the Q, sorry, don't finish it.
I just don't know why the 10 mole has actually explained less variance than the 8 modes. The 10 mode has only 0.98, but if you use 8 modes, they are actually express more of the variance. This is having correlation.
There is nothing which would ensure convergence if you increase the number of modes. It's unfortunate. I mean, in the end, if you would go to do higher and higher, then you would hope that it actually converges itself. I mean, the original system has a few hundred modes, and we just take 10. So I mean, I don't think you can hope that it actually already converges at those low locations.
This is only the correlation, pattern correlation, or the
Yes, it's only the correlations which that's for 10 modes. Yeah,
Okay.
That's just the correlation between those two patterns. And, I mean, that's also very, very high, so maybe it's also just some numerical issue or sampling issue.
How is this model now simplified? Is it the time step is longer, or you can?
You mean
What's
this?
the advantage of running the new model?
Right, this model has a few hundred modes, or decrease of frequency. This here just has 10.
Yeah, but there's a computational time. You reduce the computational
Yes.
time.
Yeah. I think for 10 modes probably would be a factor of 5, 6 or so.
Okay, so you can.
I mean, because we have this cubic term here. If I go to truncations of about 20 modes, then I think this stochastic model actually would be more expensive than the QG model, because we don't really have a fast transform to do the nonlinear calculations for the stochastic model, but we have really the fast transform for the QG model.
But the QG model is a deterministic model.
Yes,
And the stochastic model is not a deterministic model.
yes.
So what picture are you showing there? Are you showing the mean field from the stochastic model?
I have, say, for this plot, I mean, I have the evolution of the first 10 EOFs from the stochastic model equation. But I can then take the EOF canons to calculate the variance.
But the stochastic model has diffusion in it, so its output is indeterminate. That's what I mean by stochastic model. So when you run it again, you get a different answer.
But the statistics going to converge to the solution.
Right. Okay. So you have an ensemble of runs of your stochastic model, and that is the ensemble mean.
I assume it's ergodic, so I can either run a very long simulation or whatever. Or so, I mean, you can also say that the ensemble mean or the ensemble mean of the variance. But in practice, I just had one very long simulation.
So you're doing a steady state simulation, and you run it. So the forcing it's an autonomous system with no time varying forcing, and you run it for a really long time.
Yes.
And then you average the trajectories to create the picture.
Yes. I mean, I neglect to say, I don't know, the first 10,000 time steps, and then just average over the next 100,000.
And with the QG model, which is deterministic, you basically do the same thing.
Yes.
Right. Okay. So the averaging periods are the same for both of them.
Yes.
Except the QG model has got deterministic chaotic behavior.
Yes.
Yeah. And the stochastic model has got stochastic chaotic behavior.
It has both stochastic and deterministic chaotic behavior.
Okay. Got you. Thank you.
The next thing we looked at is how well the stochastic model reproduces the autocorrelation timescale. And you can see that it's not perfect, but we get for most modes roughly the same integral value over the autocorrelation function. And if we go back here, if we kind of roughly estimated the amount of timescale separation in the system, then it's, if we go to 10 modes, then it's about 0.8, so epsilon would be 0.8, or if we say 4 or 6 modes, then it's 0.5. So we are here really in the situation that we only have moderate or even no timescale separation, which you should also keep in mind. And if you look at those figures to evaluate the performance. I mean, when the whole procedure is only valid in the limit that we really have time-scale separation. I think that the model still does reasonably well in a situation where it's not really supposed to work. Okay, then we can also look at what kind of important interactions we have in the QG model, and there we can do some studies where we basically remove certain interactions terms or keep others, and then we see that the linear interactions of the unresolved modes with the mean state are very important in the attraction of grounded modes by the unresolved modes. And as I already mentioned, the QG model has about 600 degrees of freedom, and we reduce this to only about 10. Okay, just to wrap up quickly, I kind of introduced the systematic way how to derive stochastic reduced models from a high-dimensional model in a systematic way. And in the QG model, the effective, or in general, the effective equations have a deterministic nonlinear contribution of both additive and multiplicative noise contributions. And for the QG model, the reduced model simulates the climate statistics reasonably well. Thank you very much for your attention.
What about conservation of modes? For instance, typically both the sum of the total model for frost and snow modes, you might know that they conserve energy, or in an ocean model, the total amount of salt is preserved. So we don't want this stochastic small stone model term to put in extra salt.
That's why we use total energy norm UF. They conserve. Then every UF truncation would then also conserve total energy. And this also then leads to the stochastic model's nonlinear state. I mean, you can't really prove that the stochastic model conserves energy at each time step. But you can basically prove, because we will use the same mean, the same variance, more or less, that it's effectively is at least on the same attractor. Does this answer?
Can you say again what is the minimum knowledge of high frequency motion you must have in order to be able to what must you know about the small scale high frequency motion stuff?
I need to know the correlation function or the small scales and the variances. And that's probably also properties of the system which are usually not very accurate to determine. I mean, it's kind of an academic example. We have this QG model, and we can just run it for very long time so that we can really estimate each EOF mode very accurately, and then we can calculate the variance. If you really want to apply this to an IPCC class model, that would be a tough job. But at least it gives us some idea if we plan to do some kind of stochastic parameterizations or try to consider stochastic model to data, then it already gives us some idea of how the functional form should look like. Now we could use some, I don't know, particle fit or some other data assimilation procedures to actually estimate those terms from the slow modes, which hopefully would actually produce a much better model.
So, to the question, you did a very long run of the QG model.
Yes.
And you used that to estimate the EOFs.
Yes.
That contain the spatial structure for your
Yes.
modelling. Now, and those EOFs turned out, unfortunately, well, slightly unfortunately, not to have a clear separation in timescales.
Well, the EOFs only maximize the variance. I mean,
Yeah, sure. So the question is there a different spatial representation of your process that would actually have better scale separation? I mean, could you go out hunting for an appropriate basis?
Under the so-called optimal persistent patterns, because they order the patterns according to the persistence property, that they might be an attractive alternative. But there is a study where they actually showed that if you would do some low order modeling, that they actually perform worse than EOS. You would ideally you should capture patterns which kind of explain or capture the dynamics. If there would be something like the slow manifold or low order manifold, that you find modes which kind of really explain this manifold, and then you would have all the remaining modes which would explain the orthogonal or whatever of the non-manifold. But
we don't know how to do that.
I don't know.
No, I don't think
maybe you know.
No, I don't think so. No, I think it's really. I suppose the difficulty also about hunting for different types of basis is that the nice thing about the EOFs is you can manage to construct them in conservative form.
Yes.
You still need to deal with that problem, don't you?
We also need to have timescale separation, which is, I don't think really valid, say, in the climate system. If you maybe go to molecular dynamics, then that there might be more hope that you have timescale separation. Those methods might work better there, but say for the climate system, there is probably not much hope to find any clear separation between timescales, and then you might not need to worry too much about the patterns or the methods you use to construct the pattern.
Has this approach been tried on other physical systems? I mean, just homogeneous turbulence, homogeneous four-dimensional turbulence.
Yes.
What will you object?
I'm not aware of any study to turbulence. But I think studies have the problem with the lack of timescale separation.
When you said the forcing is taken from observation, you just mean the RMS value of something which would enter as a forcing? Or what exactly do you mean by taken from observation? What do you mean locally, yeah?
I start with a random forcing term. Then basically I integrated the model forward for, I don't know, 1,000 time steps or time units. Then I compared the mean with the reanalysis mean. And of course, then they will be different. Then I changed the forcing in such a way that I get closer to the reanalysis. I mean, it's kind of a nudging.
So this forcing is time invariant.
Yes.
It's a constant. So without even seasonal cycles.
It's just for the winter season.
That's for Haley forcing. You just relaxing towards the observation.
Yes.
It's rather standard.
And that's only that we get some realistic circulation. We don't aim or make any claims that this model wouldn't explain anything really in nature.
I just want to. It seems to me so it's not. Such a system may not be able to have a. It's the nature of the system that you can't find a distinct time scale separation.
Yes, but also if you look at nature, then.
Well, the nature has the sun, so it has of course it has a distinct mode like seasonal cycle and
yes.
But this I guess it's just a chaotic system you can't find.
But it must be to some extent an empirical issue. Otherwise, Christian wouldn't have to get the EOFs and then plot their AR characteristics and then decide at what point to make the computation. You could imagine that with a different set of EOFs, those pictures would have looked different.
Possibly,
I mean, I agree that the climate system doesn't appear to have any obvious separations, and that's also true in the failure record there. You know, when you look back over the last million years. But if you just lay down an equation system on the board like that, it's quite possible that under certain configurations of the forcing, for example, you might find empirically that there's separation in the appropriate basis.
I think you could confront the forcing which would then lead to a time-scale separation by just having slow forcing for some modes and fast forcing for other modes. But I mean, then you wouldn't get anything resembling climates.
So let's ask, you mentioned at the beginning that the parameterizations in deterministic models have this problem of when change the resolution. Can this method somehow help to resolve these kind of problems?
It gives us some ideas how you might, or with which functional form you might start, but I mean that's more or less a, say, diffusion process. If you think about convection, I mean that's not really a diffusive process, it's probably more like a birth-death process. You either have a convecting cell or you have it not, because it didn't overcome the inhibition. So if you only try to represent better, say, turbulent eddies, then that might be a way to go.
In your formulation, you started with assuming time-scale separation,
Yes.
and assume epsilon is small.
Yes.
And then you applied the epsilon for 1.
That's just
in the previous slide. Could you go before for your demonstration? Yeah, that one. Next. So you truncated the epsilon expansion at some level.
Yes.
And then next slide. Could you go next one? Yeah, that one. So you applied it to epsilon equal 1. And
It's still, that's,
so you truncated epsilon expansion, did you?
if you do the general case, then
Yeah.
basically
Yeah.
that's what you do.
Yeah, it's like a closure in
Hmm?
turbulence. It's a closure in turbulence study.
Yes.
And people know that in some case, expansion in powers of some parameter may be truncated safely in the context of renormalized expansion.
Yes.
So, assuming epsilon to be small, then truncate, and then substitute for epsilon equal 1. That is, in the case where no time-scale separation. Then, next slide please. The closure may work up to that kind of extent.
I mean, that's
The
Say
case,
it's supposed
yeah,
to work.
it's supposed, but A
Right.
is not supposed to be correct, but may work still, to some
Yes.
extent.
I mean, to some extent it's
Yes.
still works.
So even without any time scale separation, to give some answer.
Yes.
Yeah.
I mean, the question was brought up earlier about the connection with aspect of homogeneous turbulence, where you don't have the separation of timescales, but you might do it anyway. So would the introduction of noise correspond to what you would call backscatter in turbulence? Which so you would have the closure model, which cuts off the evolution for the higher wave numbers and short time scales, but you would need to restore the
If it's in climate models, then you usually just introduce some kind of damping term to represent the unresolved increase of freedom. In that sense, you could say that the stochastic term kind of backscatters some of the energy back into the resolved mode.
Yeah, exactly. Yeah.
And that's what Glenn Schultz has done, isn't it, in his stochastic backscatter?
Yeah.
He's propagating noise back up the system in exactly that way. And there is a stochastic component in the ECMWF framework, I think, isn't
Yes.
for ensembles.
And has that been studied under the more well-studied simple isotropic homogeneous turbulence conditions?
I think that the original idea is from turbulence. I think they also have some stochastic backscatter model.
But in the context of turbulence study, it's like just Lenzheimer expansion. That is, linear term is dominant in that equation.
Yes.
So epsilon corresponds to Lenz number, and it's essentially Lenzheimer expansion and truncation and discard for the higher terms. And then it's safe for small epsilon, but extend it to non-smaller number may work sometime. Very similar to turbulence structure.
Any other questions? If that's not the case, then let's think again. And we'll prepare now the stage for barbecue outside. We have a grill and our meat, and wine and beer. So that should be the celebration of the Swedish summer here.